Have you ever just stopped and wondered how a simple idea in your head actually becomes a real working app on your phone? Well, today, that's the exact journey we're going on. We're going to follow that little spark of a concept all the way until it's a program a computer can actually run. We'll break down the fundamental building blocks of code, one piece at a time. So, this is really the big question, isn't it? How do you take a goal, something like, hey, let's calculate a student's grade average, and translate that into a super precise set of instructions a machine can follow perfectly, without any mistakes, every single time? That whole translation process, that's what programming is all about. You know, the first challenge you always run into is scale. A big idea is kind of like someone telling you to just build a car. I mean, where would you even start? You can't just grab a wrench. You have to break that massive task down into smaller, more manageable pieces. Design the engine, then the frame, then the wheels. And this quote right here just nails it. The real secret to tackling huge, complicated programs isn't about being some kind of super genius, it's about being organized. Honestly, almost everything about software development is about finding clever ways to create these manageable chunks. So, our very first tool for making these chunks is the subroutine. The best way to think about it is like a recipe in a cookbook. Instead of writing out all the steps for, say, drawing a house every single time you need one, you just create one master recipe, one subroutine, and you name it Draw House. Now, anytime your program needs a house, you just say, hey, run Draw House, and the computer knows exactly what to do. It's the absolute core idea behind organized, reusable code. Okay, so we've broken our big idea into smaller chunks. Great. Now we have to actually write those chunks down in a language the computer gets. And just like any language, English, Spanish, you name it, this one has rules. It has grammar. You have to know how to build a valid sentence, or in our case, a statement. Let's start with the nouns of our programming language. We call these variables. Just picture a labeled box sitting in the computer's memory, and it's built to hold one piece of information. So when we write rate equals 0.07, we're basically telling the computer, hey, make me a box, label it rate, and put the number 0.07 inside. That's it. From now on, whenever we need that number, we just use the name rate. But here's the thing. The computer needs to know what kind of information we're planning to store. I mean, you wouldn't try to store soup in a paper bag, right? That's where data types come in. An int is a box for whole numbers. A double is for numbers with decimals. A boolean holds a simple true or false. And a char holds just a single character. Telling the computer the type is so important. It tells it how much space to set aside and what kind of things you're allowed to do with that data. This slide is just perfect because it shows you exactly how a computer thinks. It's incredibly literal. Look at the top example. It sees the text test first. So it decides everything that follows must also be text. It just glues the 2 and the 3 onto the end. But in the bottom one, it sees 2 plus 3 first. It says, oh, that's math. It calculates 5, and then it sees the text and glues test on. It follows the rules perfectly, which shows how just changing the order can totally change your result. All right, so we have our nouns and our grammar. Now it's time to build sentences that can actually think. We need to give our program a way to make decisions and to do repetitive stuff without us having to write the same line of code over and over and over again. The most basic tool for decision-making is the if statement. You can think of it just like a fork in the road. The program is chugging along, it hits this decision point, and it asks a simple true or false question. For instance, is the grade 90 or higher? If the answer is true, it goes down one path and does something. If the answer is false, it just keeps on going down the other path. This simple little choice is the foundation for all complex logic in a program. And for repetition, we use things called loops. Now, a for loop might look a little complicated at first, but it's really just a tidy way of answering 3 simple questions. First, where do we start? We initialize a counter n to 1. Second, when do we stop? We keep going as long as n is less than or equal to 10. And third, what do we do after each cycle? We update n by adding 1 to it. So in one clean little package, we've told the computer to count from 1 to 10. Okay, get ready, because we're about to make a pretty big conceptual leap. Up until now, we've basically been writing to-do lists for the computer. But a lot of modern programming takes a totally different approach. Instead of just writing down procedures, we try to create digital models of actual things from the real world. And you might be asking, well, why? Why do it that way? This quote gets right to the heart of it. This idea is called object-oriented programming, or OOP. And it makes sense when you think about it. We don't experience the world as a giant list of instructions, right? We see it as a collection of objects, people, cars, bank accounts. Each of those things has its own information and can do its own actions. OOP is all about modeling that reality right inside our code. So how does this actually play out? Well, on the left, you've got a design for a single, shared piece of data. Think of it like a public bulletin board. There's only one, so only one person's info can be up there at a time. But on the right, we have a class, and a class is like a blueprint. Think of that blueprint as the design for a student. From that one blueprint, we can create tons of individual objects. Each student object is built from the same plan, sure, but each one gets its own separate space for its own name and its own grades. That is the core of OOP, designing reusable blueprints to stamp out countless unique digital objects. So, we've designed our logic, we've written our code, but right now, it's really all just text sitting in a file. It doesn't do anything yet. For the final leg of our journey, let's look at how we actually bring that text to life so it can run on a computer. It's basically a three-step dance. First, we write our code in a way that we humans can read. Second, a program called a compiler acts like a translator. It turns our code into an intermediate language called bytecode, which you can think of as a universal dialect that lots of different computers can understand. And finally, an interpreter on the actual computer reads that bytecode line by line and carries out the instructions. So with all this code, where does the interpreter even begin? It looks for one very special subroutine named main. This is the designated front door, the entry point. It doesn't matter if you have 1,000 files and 1,000,000 subroutines, main is the starting pistol that kicks off the whole chain reaction. It's always the very first thing the computer runs. So we've done it. We followed an idea all the way from a little spark to a fully working program. We get the mechanics now, subroutines, variables, logic, all that stuff. But this brings up a much, much deeper question. You see, it's one thing to make a program that just works. It's another thing entirely to make a program that is correct, that's robust, efficient, and easy for other people to understand and change later. And that, well, that's the whole art and science of software engineering. So what do you think really makes for good code?